I'm Steve Draving. I'm a hardware architect on the new modular test system for quantum computers. My background is very simple. I've done the same thing for the last 35 years. I've designed high-performance test equipment for Hewlett-Packard, and then Agilent, and then Keysight. Most recently, I was the time-based architect on the UXR 110 gigahertz real-time oscilloscope. We design our equipment to be very stable in hardware, and we do things specifically. We use special materials, and we lay out PC boards in a certain way, and we do a variety of things to make the hardware physically stable as we can. But then, after we do that, we apply a lot of error correction. We do lots of temperature characterization and humidity characterization, and then we apply error corrections to make it even more stable. We have a chamber downstairs that we use to measure the radiated emissions of our products and make sure that they're not too susceptible to other radiation from outside, RF kind of stuff that gets in and messes up your measurements. The biggest challenges really are trying to maintain coherency and stability over the massive scalability of this product. Maintaining coherence across 4 channels of an oscilloscope is one thing, but across 1,000 channels of a system that's spread across multiple racks 6 feet apart, that's a major challenge. It's not only spatially across many, many channels, but it's also across duration of time. So we're trying to maintain coherency in the picoseconds across 1,000 channels for an entire second, and that's really difficult. A key piece of technology that we're using is a clock module developed by Keysight Labs that's very low phase noise clock reference. Well, we were able to leverage that technology and put that into this system, and that gives us very good long-term time stability. And then we take that as kind of the source clock for our time base, and then we multiply that up in frequency to drive all the samplers and our digitizers and our AWGs. And we do that through specially designed cables that don't drift with temperature and circuits that are designed to have very low phase noise and low phase drift. And all of that contributes to maintaining low jitter in the system. Another cool piece of technology we leveraged from Keysight Labs was a very sophisticated DAC IC, or digital to analog converter IC. And not only can it generate arbitrary waveforms, but it can perform IQ modulation with digital upconversion. The way we use it, we can generate signals with 2 gigahertz of bandwidth, and we can put that 2 gigahertz of bandwidth anywhere in DC to 16 gigahertz frequency range. The real advantage of the digital upconversion is that with conventional analog upconversion, you have to use LOs and mixers, and you have to get all of these clocks phase aligned with the waveforms that you're generating. And then you have to maintain gain stability and frequency stability, phase stability between all the pieces of the upconverter, of the mixers. But with digital upconversion, all that is handled digitally, so you don't have to worry about the calibration and the stability of the mixing process. And another cool thing about digital upconversion is that conventional upconverters, if you have to change the LO frequency or you have to change the LO phase, it takes some time for that to happen because you want those LO signals to be very stable. And so to make them stable, you have to design them in a way that doesn't allow them to change quickly. But with digital upconversion, you basically can change the LO frequency or phase almost instantaneously.